This video contains two examples around inference for two proportions. The first one is a confidence interval example. The second is a significance test example. You should watch both and pay attention to some of the differences in the calculations and how we treat assumptions in both, because there are differences that are important. The first is a confidence interval. Keep in mind here, our goal of this confidence interval is to estimate some population proportion that we don't know. A difference in population proportions that we don't know. Like all other confidence intervals, this one is made up of an estimate. In this case, it's an estimate of the difference in proportions based on two sample proportions. A critical value, which tells us how many standard errors to put into our margin of error. So we have an estimate plus or minus a margin of error. Right, why don't you read this question, pause me, and why don't you see if you can get started on panic for this, see if you can make some sense out of this or think it through. It doesn't say, let's assume this is a 95% confidence interval. We're being asked how large is the difference, so we're going to make an estimate for that. So pause me, read this, give this some thought based on the prior lesson and the formula I just showed you. All right, well, I'm going to assume you took a shot at that. This is a panic problem. So let's walk through the steps here. First off, we're being asked to estimate a difference in proportions of men and women who are still living at home with their parents. So you can see the symbolism here. We're estimating. Here's our difference in proportions. Notice I've used little m and little w to help keep things straight. So we're estimating p little m minus p little w, the difference in the proportion of men and women age 19 to 25 who still live at home. Remember, the point of this p step is to define the variables, p little m, p little w, define them, not just write them. Define the variables in the populations that you're dealing with. Right? We have assumptions we need to check here. So we have two random samples that's given to us. The independence check, it's reasonable to assume that there are more than 22,500 and 26,290 men and women nationally, so we can assume those in each group are independent of each other. And then it seems reasonable to assume here that the sample of men and women are independent of each other, since it appears they were taken from a national sample. Now, the normality check, the sampling distribution of the difference in sample proportions has to be approximately normal. Now, I've used the success-failure language here. We have more than 5 successes for men and women, 986 and 923, taken from here. And then if we subtract the successes from the sample size, we get the number of failures. Now, this is the equivalent of doing n1 times p hat 1, n1 times 1 minus p hat 1, n2 times p hat 2, n2 times 1 minus p hat 2. So what you see here is the equivalent of that, and is acceptable. It just saves us some writing and and a little bit of calculation. So our sample sizes are both big enough so we are comfortable with normality for the sampling distribution of proportions. This is a 2-proportion confidence interval, 2 not 1. We're dealing with 2 proportions. All right, and I then is the actual calculation of the interval. So you're always going to have to show your work for this. And we need a few things. I don't know what p hat 1 and p hat 2 are yet. So let's do that. Let's go do the men first. P hat for men, 986 men out of a total of 2253. And if you do that calculation, you get 0.4376. And then for women, we have 923 divided by their sample size, which was 2629. And if you do that math, you get a proportion of 0.3511. Right, so then we can set up the confidence interval, p hat 1 minus p hat 2. You have to show this work to show you understand the mathemagic of what your calculator can do for you. Plus or minus, we said it was going to be 95%. It's z, so that's 1.96. And then we need to get this detail right. This is p hat 1 0.4376 in the standard error calculation, times 0.5624, 1 minus p hat male, divided by the male sample size, 2253, plus p hat female, times 1 minus p hat female, 0.6469, divided by the sample size for females, which was 2629. Now, do not, under any circumstances, do that math by hand. On your calculator, there is a 2-proportion z-interval, and it will ask you for successes and failures for both samples, so you enter in whole numbers for that. You do that in this case, you'll get this, confidence interval of 0.059. The difference in population proportions that we're looking for lies between 0.059 and 0.114. Then your conclusion should be make use of that interval we just came up with, and let's try and do it in a way that's more easily understandable. So let's say we're 95% confident that 5.9% to 11.4% more men live at home with their parents than women. How do I know it's more men? Because of the way I subtracted men minus women and the fact that both of these numbers are positive. So you do have to pause and give some thought to the proportions you came up with and how to properly interpret them based on the way you subtracted and based on the signs that you come up with. So that's a confidence interval. Note the format for calculating standard error, the square root here, and note how we check for normality using numbers of successes and failures, or n times the p hat values. Okay, the second example we're going to do is a significance test. A reminder that in this case, this slide comes from the prior lesson video. We're not going to use that standard error formula anymore. We're going to use this idea of p hat combined. So when we do standard error here, this is the formula that we're going to use. We've replaced the p hat 1s, p hat 2s with this p hat combined calculation, which is a single fraction where successes are added in the numerator and sample sizes are added in the denominator. So here's an example. There's evidence that high blood pressure is associated with increased risk of death from cardiovascular disease. A major study of this association examined 676 men with low BP, 3338 men with high. During the period, 21 of the men with low blood pressure and 55 of those with high died of cardiovascular disease. Does this study confirm that death rates are higher among men with high blood pressure? So let's organize our data a little bit. The low blood pressure folks, we had 21 die, and of the high we had 55 die. There were a total of 676 with low, so that means 655 didn't die, and there were a total of 3,338 men with high blood pressure. Of those, 55 died, which means 3,283 didn't. So that's the data we're going to use for this significance test. So with that information, this is a phantoms problem. Why don't you pause me here for a moment and see if you can work through some of the steps for this problem. All right, assume you did that. We're looking for a significant difference in these death rates. Is the death rate higher for men with high blood pressure than it is for men with lower? So here we're not estimating. Let's keep in track what we're doing here. We're testing for a difference. Now, you can subtract either way here, but I suspect it's higher. There's a higher proportion. I know there's a higher proportion in the sample for men with high blood pressure. So I'm going to do the higher proportion minus the smaller. I end up with a positive number. It's a little easier to think about a positive difference in proportions. I also think this is more close to the question being asked. So we're testing P little h minus PL, the difference in the proportions of men. I didn't switch it here. This should be high, and this should be low. The difference in proportion of men with high blood pressure and men with low blood pressure who died due to cardiovascular disease. Again, I've used symbols on the proportions to help keep things straight. I've defined what the P's stand for, and I've told you what populations we're dealing with. Here are my hypotheses. The first is that there is no difference. The second, again, we have to read the question carefully to know what inequality to put here, but we're testing for a higher proportion for men with high blood pressure than those with low. Checking the conditions here, it's not completely clear if we have two random samples, so we'll need to be careful generalizing. Our normality check, we have to make an assumption that each of the populations is 10 times each of the sample sizes, and then we're going to say it's reasonable to assume that men in the two samples are independent of each other. That seems reasonable. Now, the normality check here. I want to walk through this. This is an example. It's a significance test, so we're going to use p-hat combined in the normality check here. And p-hat combined is the sum of successes, 21 plus 55, over the sum of the sample sizes, and that's our calculation for p-hat combined. And if you do that math, you get 0.0151. So our normality check here is each individual sample size times p-hat combined and 1 minus p-hat combined. So for the first sample, those turn out to both be greater than 10, and then we need to do that for the second as well. So our check uses p-hat combined, not the individual p-hats for high and low blood pressure. And that's a critical difference here that will be looked for when doing a significance test versus a confidence interval. This is called a two-proportion z-test, only z for proportions. And then we need to calculate our test statistic. So the test statistic in the numerator, we have our estimate of the difference, p-hat high minus p-hat low. So we need both of those calculations. So for p-hat for low blood pressure, start over here. Let's do high first. P-hat for high blood pressure, we have 55 over 33, 38, and that turns out to be 0.0165. And for low, we have 22 over 1676, which turns out to be 0.0125. So the numerator for our test statistic is the difference in sample proportions, p-hat for high blood pressure minus low, divided by standard error. And because it's a significance test, we use p-hat combined here. So in the numerator, or in the denominator here, we have p-hat combined times 1 minus that, times 1 over the individual sample sizes. Sample size 33, 38, plus 1 over 1676. Right, and if all that work is done carefully, we end up with a test statistic of 1.079. Now again, do not do this by hand. Use the two-proportion z-test available to your calculator. To do it by hand only opens you up to the possibility of making an error. From this, the calculator will also give you a p-value, right, which is also a normal CDF calculation, 1.079 to something large. We'll use infinity, of course, and if you do that, you get a p-value of 0.1403. So that's a relatively high p-value, and with that, we're going to draw the following conclusion. And because the p-value of 0.14 is high, we have insufficient evidence to conclude that the proportion of men with high blood pressure who die from cardiovascular disease is higher than the proportion of men with low blood pressure. So when you get to the conclusion, you have to keep in track of the order in which you subtracted and keep track of how you set your alternative up, and then always close by discussing your alternative hypothesis after looking at the p-value. There's a bit more to this example, maybe 5 minutes at the most, so when this video is done, start up example number 2. There's one more minor thing I'd like to go